Every second, the sun releases more energy into the vacuum of space than humanity has consumed in its entire history. It is Earth's most abundant, unlimited, and powerful energy source. The fraction of this output that successfully crosses the 93 million miles to our planet is what we classify as solar energy. Before this incoming radiation interacts with Earth's atmosphere, its exact power output can be mathematically quantified. Scientists and engineers refer to this specific measurement as the solar constant. If you place a 1 square meter surface in orbit, perpendicular to the sun's rays, it receives an energy influx of 1,367 watts per square meter. This represents the absolute maximum power potential available per unit of area, before atmospheric absorption or scattering causes interference. This 1,367 watts per square meter influx provides a completely free, renewable, and pollution-free baseline of power. The central engineering challenge is how to effectively capture this constant stream of radiation and convert it into usable electrical or mechanical work down on the surface. As we shift our focus from orbit down to Earth's surface, that initial 1,367 watts per square meter does not reach the ground intact. In a terrestrial context, solar radiation refers to this incoming light energy as it scatters, reflects, and changes upon striking the gases and particles in our atmosphere. This diagram shows the 3 specific types of radiation engineers must account for. One strikes the ground straight down as direct radiation, another scatters off clouds as diffuse radiation, and a third bounces up off the terrain as reflected radiation. To achieve maximum efficiency, energy capture systems must be explicitly designed to utilize all 3 of these light behaviors. The first of 2 main architectural solutions for capturing this energy is the solar thermal system. The primary mechanism of a thermal system involves using large arrays of collectors to concentrate diffuse and direct radiation, producing intense localized heat. This heat is then transferred to water, boiling it to create high-pressure steam. The physical pressure of that steam is used to spin a mechanical turbine, generating electricity. This aerial photograph shows a massive circular array of mirrors on the ground. You can see how they are all precisely angled to direct reflected radiation toward the single central glowing tower, achieving concentrated thermal power on an industrial scale. While thermal systems are highly effective for large-scale production, they rely on intermediate thermodynamic steps and moving mechanical parts. This creates the need for a more direct, solid-state solution. That alternative architectural pathway is the solar photovoltaic, or PV system. The primary distinction here is that PV systems skip the intermediate steps entirely. They convert sunlight into electricity without the need to generate heat or steam. The foundational component of this system is the solar cell, shown here in cross-section. The core material is explicitly labeled as a silicon semiconductor. Silicon is chosen specifically because its atomic lattice structure is highly reactive to the specific wavelengths of solar radiation. The process begins when sunlight, acting as packets of energy called photons, physically strikes the surface of the silicon cell. This triggers a quantum reaction. The energy from the incoming photons transfers to the electrons within the silicon, causing them to excite and break free. The cell is engineered with specific positive and negative layers, which create an electric field. This field forces these free-moving, excited electrons to flow in a single, continuous direction. This unidirectional flow is what generates direct current, or DC, electricity. This specific model of electron excitation serves as the standard conceptual framework for technical assessments of solar physics and semiconductor behavior. Photovoltaic systems bypass the mechanical complexity of traditional power generation, extracting electrical current directly from sunlight using stationary, solid-state materials. The primary physical limitation of a single solar cell is that, by itself, it generates a relatively tiny amount of power. To solve this, multiple individual solar cells must be combined. By wiring them into a grid, like the distinct blue cells on this structure, they form a panel capable of measurable power generation. Translating this modular technology into a globally viable power grid requires evaluating a strict set of physical and economic constraints. The operational advantages are clear. Once installed, these panels offer an unlimited, pollution-free source of energy that demands very little ongoing maintenance. This chart contrasts benefits with inherent disadvantages, high initial costs, and weather dependence. Because the 1,367 watts per square meter is spread out, generating massive power requires extremely large areas. Furthermore, since output drops at night, large-scale batteries are required for continuous supply. Deploying solar infrastructure is an engineering balancing act. We must weigh the high upfront capital and vast spatial requirements against the yield of decades of free, low-maintenance energy. Despite these constraints, the structural strength of solar energy is its absolute scalability. It functions effectively on massive infrastructure down to tiny consumer devices. It holds a unique advantage for developing infrastructure in remote areas, where laying traditional electrical grids is geographically or economically impossible. Common applications include self-sufficient streetlights, agricultural water pumps, and multi-megawatt power plants. On a residential level, we see commercial applications of solar thermal capture, like this rooftop water heater. Broad flat panels heat the cylindrical tank above. We can contrast these heavy-duty applications with micro-applications that require only fractional amounts of power to operate, such as orbital satellites and small consumer electronics. This calculator is an everyday example of micro-photovoltaic power in action, utilizing a small array of 4 individual solar cells in its top right corner. Whether it is powering a pocket calculator or sustaining a vast desert grid, the entire system relies on a single continuous baseline. It all comes down to our ability to intercept that 1,367 watts per square meter from orbit and precisely coax silicon electrons into motion.